All right, so this is the video lecture on how pointers work in C++. All right, so to start us off, basically everything in C++ lives somewhere in memory. And that's any data you have, anywhere. If it's in C++ and C++ is storing it, it's residing somewhere in memory. So let's look at this program. We've got, for example, this variable a, and it just prints out a's value. So I'm going to take it over here and copy it into Emacs. All right, put these screens side by side. All right, so now I'm going to say I've got to declare int main, and then of course I'm going to include IOStream, and now I'm going to declare this variable a and say its value is 23, and then I'm just going to cout print it and say a's value is, and then a. So basically the simplest program we can write. And then I'm going to open the std namespace so I don't have to keep typing it. All right. Now I'm going to load up a compiler and compile my program and start running some examples with it. So I'm going to do a clang++ and then pointers.cpp. All right. Now let's run a.out. And of course I left out the new line, so you're going to see that a few times throughout this video. I'm going to add it back in because otherwise it's very hard for me to read. All right, and we'll run our program again. So, okay, as expected, a's value is 23. So, like I just said, a resides somewhere in memory, and that means that it has an address. So memory is a big, giant place where there are bytes that reside, right? And it's sort of addressed by using these unique numbers. All right, so let's see what I mean by that. To get the address, we use this operator AND, which you can read as address of. So now I'm going to say a's address in memory is going to be at a. All right, and we'll see where that address is stored. It's actually stored on the computer's stack, right? So all computers have a stack that they use to sort of push and pop data, and local variables for functions are stored on the stack. Now we can see here, a's value in memory is at this big long address. All right, now try not to get this notation for address of confused with a reference. References are a totally different concept in C++ that are very strongly related to pointers, but let's see an example where we're using a reference. So I'm going to define this new function foo, and I'm going to say int reference x, and now I'm going to say the value of x is, and then I'm going to say just x. All right, so even though it has this little at in front of it, it basically behaves in every single way like a variable. I can do the same thing. I can update x to be 23, or in fact, let's just update it to be x++. All right. So x here is going to be passed by reference. So what that means is that the caller of foo is actually going to see whatever thing they pass in that's going to get used for x to be updated. So now if I call foo of a, well then foo in running is going to update x to be x+1. And then because a is x here, and we're passing by reference, which is what I mean by having that little at thing, then we're going to see it as plus. Now let's look at a different example, bar, where I don't pass by reference. And of course I need to go back and change these function declarations so that they say void instead, because I don't want to return a value. All right, now let's call bar. All right, so now bar is just, it's sort of normal, right? It's not using a reference. It's just using an integer. All right, now let's add something to foo. We'll just say here, print the location of x. So what I mean by that is print the address of x, just like we did in the upper frame. All right. Let's do the same thing for bar. So I'm going to print where x is stored. And what I'm going to see is that when I'm passing normally, so when I'm not passing by reference, it turns out that the computer is actually going to copy into a new variable. All right, so, and that's why when I call bar, nothing happens, because in fact, C++ allocates new space for bar. Sorry, for x in the call to bar, I mean. All right, so let's do that. We'll call both of those functions, compile that, call it again. And I can see that, of course, the location of x, that call to bar, is going to be this new location that's distinct from this A's address in memory. All right, and that's because I use that, I didn't pass by reference. But for foo, when things are passed by reference in C++, you can sort of think of them as if they're, in essence, pointers. All right, which is the thing that we're talking about mostly in this lecture. All right. So okay, so references and pointers are related, but very different. All right, now everything in C++ has a size. Turns out we can actually look up that size by using this operator, size of. Now, even though it looks like a function call, it's actually not. It's an operator. That's kind of confusing to most people. You don't have to actually add the parentheses here, but I do because I like to use it in this sort of function-like fashion. So okay, let's see an example use of size of. Turns out you can use size of with either the name of a type, for example, int or int star, but you can also use it on variables. So let's say, see right here I'm saying the size of A, and then I say size of A. I might say the size of int is the size of int. And then the size of, let's say, double, which represents floating point numbers, is double. All right, now let's run this program and see what we get. Now, by the way, size of report its output in bytes. So if it says 4, that means 4 bytes. If it says 8, that means 8 bytes. All right, and here I'm just saying size of can either take a type or a variable as its arguments. All right, and we see, for example, that the size of A is 4, int is 4, and then double is 8. And that's pretty common on 64-bit architectures. So we can see, for example, that this integer is actually 4 bytes in memory. All right, the highest or most significant byte all the way down to the least significant byte. All right, so there are 4 bytes in memory that are used to store an integer. Now, local variables to a function are stored on the stack. And when a function has multiple local variables, that means they're stored at sort of subsequent locations on the stack. So let's take some example code right here we've got, where we basically say we've got, all right, let's see. Let's copy and paste this example code into my buffer, where I'm declaring 2 variables, 23 and 24. And I'm going to comment out this main function. I'll come back to it in a second. I'm going to just copy and paste in this example over here. All right, so now I've got two local variables to main, A and B, and I just said they'll be allocated on the stack. What I'm going to find out is, in fact, they are allocated very close together. All right, so the size of A is 4, A's value is 23, B's value is 24, B's address is this thing right here. Now they're written in hexadecimal, so it's kind of hard to read, but it turns out that these are actually only 4 bytes difference. And there is a program, Python will do hexadecimal math for us. So let's say I want to subtract and find out what's the difference between these two addresses. I can see it's just 4 bytes. All right. And another thing that's really interesting is that, in fact, B is located under A. And that's because in C++, the stack grows down. Actually, in all computers, the stack grows down. So when C++ calls a function, it creates space on the stack to store all of the local variables to that function. That's actually not quite right. It's not all the local variables in the function. It's actually the local variables in the uppermost scope. But that's roughly the idea. Is basically whenever you enter a scope, you'll create local variable space for everything in that scope. And then when you return from the scope, all right, by which I mean you exit the scope, right, return from a function, for example, then that space on the stack will get destroyed, and you'll get that will get overwritten. And that's, for example, why you why you don't, for example, use an infinite amount of stack space or something like that. And that's because, the stack will grow up, will grow down as functions are called, and will grow back up again as functions returned. So, and we can see in this example, calling bar will place an integer on the stack because bar takes one integer argument. All right, now integers take 4 bytes. So to call bar, I have to put 4 bytes on the stack. So to call that function, C++ is going to put bar on the stack and do that. Now to call foo, what are we going to have to do? Well, in C++, x is actually, since it's a reference here, it's going to be implemented by the compiler as a pointer. So to call foo, C++ is going to have to put a pointer to that variable x on the stack. All right, now it turns out that in C++, pointers take 8, what I mean is on 64-bit machines, pointers take 8 bytes to represent. So C++ will actually have to put more stuff on the stack for this reference than it would just for an integer. And then I'm also writing a note here that references in the C++ standard don't actually admit an implementation. It's just that most compilers will implement them using constant pointers. All right, so you can sort of think of pointers as the implementation strategy for references. But in the C++ standard, it's not defined to be a pointer, for example. All right, so let's see. Okay, so the lesson is the stack grows down. Let's try another example. So if I know some data's address, I can actually get the value out of that data's address by doing this operation. So I can use the star operation, which you can think of or read as dereference. So I'm going to just create I'm just going to create a value here. So if I say the value at, and then address of A is, then I can say dereference address of A. And then I can do indel. All right. And so I typically call this the dereferencing operator, or star. Plenty of people in C++ just call it star. And this is the address of operator. And, people will call that, and, I guess, or something. But I think usually people say address of, although I'm not enough of a C++ expert to know what the common term is. All right, so if I take the value, if I dereference after address of, I get the exact value back. So value of followed by dereference is just the identity. All right, so let's go back. I switched screens here. So I talked about that. I can use the star operator to get the data at some address. And I can store addresses. And these are called pointers. That's what this whole tutorial is about. And it turns out that the type of a pointer is this thing with a star in front of it. So if I say int pointer to A, and then I put a star in front of it, well, that is in fact a pointer to an integer. All right, so whenever something has a star to the right of it, it means it's a pointer to that thing to the left of it. All right, now in general, the C++ pointer syntax gets pretty confusing, especially when you factor in things like arrays and function pointers and stuff like that. But this is a general strategy you can use when you're learning C++. If you want to become an expert, you're going to have to read more. All right, so just as I can do before, if I say pointer to A is, well then the value of pointer to A, which again is also another variable, just like the value A is a variable, pointer to A is also a variable. I can say the value of address at A is 23. The pointer to A is, and then this big number. All right, so if data D is of type T, then at D is of type pointer to T. Yeah, I made a mistake here when I was writing, but it's of type pointer to T. So what would the type of at pointer to A be? I'll let you think about that for a second, and then you can keep moving on. Turns out it is pointer to int. All right, and here's how we can write that. All right, so let's declare a new pointer to, what I actually want is pointer to A, not pointer to A. Pointer to A is at, and then not pointer to A, that would be a self-reference, pointer to A. All right, there we go. And then I can do cout, pointer to A is, and then, in fact, that is the address of the pointer to A. And it turns out I can do this again. Pointer to A, and then I can prefix this with another at. All right, and then remember, let's run this program, but remember that just because these are pointers doesn't make them special. They're still just variables that are going to be stored on the stack. So let's run this program and see what we get. And then, of course, I left out my new lines, so let's go add those in. All right, I didn't recompile. That's what the problem was. All right, run a.out. Here we go, perfect. So you see pointer to A is this value right here, and then pointer to A is in fact only a little bit lower than that, 4 bytes off from that, I think. All right, so not very far. And that's because all those things are stored on the stack, right? Because all local variables are stored on the stack. That's just how C++ works. And most languages work, is that whenever you enter a new scope, which in this case, our functions don't have any subscopes here. But when you write more complex functions that have, for example, if blocks that then define their own variables, well, whenever you enter that block, then you will naturally create a new scope. We'll talk a little bit about that later as well. All right, so now all pointers take up the same number of bytes, and this depends on what the machine you're on is, sort of depends on what machine you're on. So now let's see what a size of an int pointer is here. We might try pointer to int, but it turns out that the right syntax is actually int pointer. All right, so if I try to compile it this way, C++ is going to tell me I have an error. And that's because the syntax is wrong. It's int pointer. All right, so a pointer to an integer. All right, and let's go down here and run that again. Size of int star is 8. All right, so the native pointer type on my machine is 8, and that's because I'm on a 64-bit machine. And in fact, the reason it's called a 64-bit machine is because pointers are 64 bits, meaning you can address 64 bits worth of memory. Turns out if you run the numbers on what a 32-bit pointer can represent, it can actually only point at 4 gigabytes of memory. All right, so that means you can't use a single program that talks about more than 4 gigabytes of memory if you're on a 32-bit machine. Now, maybe you could have more program and different programs, more RAM and different programs talk about different segments, but that gets sort of complicated. There are different extensions that do that. So now let's see something bad. What happens if you return a pointer to a piece of data that's declared on the stack, right? Because everything we've talked about so far has been declared and put on the stack. Well, okay, let's think about what's going to happen. I'm going to draw some boxes out here for the different stacks that represent the program as it evolves. So first up here, we've got a stack for do something bad. All right, and do something bad is going to call returns a bad pointer. All right. All right, so let's draw some arrows. This is going to be the stack going down. All right, so label this. This is the stack. The stack grows down. Every time a function gets called, a new scope will be entered. And so there's going to be new stuff allocated on the stack. All right, so returns a bad pointer is then going to be called here. That's going to create a new scope or a frame on the stack. So returns a bad pointer. And then inside of the frame or the data for returns a bad pointer is going to be this local variable a, and then also this other local variable ptr. So let's write them out. We're going to write them next to returns a bad pointer because that's where returns a bad pointer is going to put its data. So I'm going to take I'm going to write out both PTR and A right here, because that's the place that they're allocated. They're allocated at that stack frame, returns a bad pointer right under do something bad. Okay, so what happens now when returns a bad pointer returns? Well, this is where the problem is, because when returns a bad pointer returns, its place on the stack basically goes away. And all the data that was previously stored there is now going to be overwritten. All right, it's kind of like when you delete a file on your operating system, it gets marked for deletion. It's not immediately overwritten, but it's sort of unsafe to assume that that data is has the same integrity it did before. Because when returns a bad pointer finishes, the stack is going to get popped back up so that other functions can get called. All right, so it's sort of going to go away. That's why I turned the opacity down right there. I'm going to draw a big red X on it now, signifying the fact that returns a bad pointer is now totally over and all of its data is dead. All right, so let's take a second to actually read what this code does. First, it stores 23 in the variable A, and then it's going to take a pointer to it, and we would expect that if this code were working correctly, after it returned that pointer, the value stored at that pointer won't change. But we're going to see that in fact it does, and that's why it's so unsafe to run this kind of code. All right, so first I have to recompile it, and then I actually have to call the function, do something bad. All right, and it's actually going to give me a warning saying address of stack memory with local variable A returned. All right, so I can see down here in the bottom right, it says the value of PTR is 23. And then the second time I print it, it says the value of PTR is 32767. That's because that value A, whose address I took, was totally written over by the call to cout. All right, so the call to cout actually allocated some space on the stack that changed the value that used to be A. So that value had then been trashed. All right? So the lesson here is that once a function returns, the pointer is meaningless. And if I keep using it, I can actually cause a bunch of problems. Some of them are actually security problems. So how can I hold on to things after I return? Turns out I can use the heap. Now, unlike the stack, when I put things on the heap, they don't go away. So let's copy some code here that's going to do that. All right, so I'm going to make this function new pointer that allocates something on the heap by using the keyword new, then sets it to 23 and returns that value. And then I'm going to increment that pointer, and then I'm going to display its value again. All right, so let's see, do something fine. We're going to be using new here, and then note that I'm also at the end of do something fine. So this is bad code up here. This is good code down here. Allocates on the heap by using new. Notice that at the end of do something fine, I'm also calling delete PTR. That means get rid of the memory space that I had allocated previously. If I don't do that, I'm going to run into big problems. All right, turns out I didn't have any of indels here, so I'll add those. All right, and I can see the value of PTR is 23, and then the value of PTR is 24. Okay, good. So notice here that I specifically had to say delete PTR. That means let the memory go. So if I ever have data that's allocated with new, after I'm done with it, I have to call this operation delete, which is an operator in C++ just like size of. I have to call delete very explicitly. All right? If I don't call delete, the memory will never go away, and it's sort of going to live on forever. So let's look at this example here, use all my memory. You notice the problem here is that I've got this pointer PTR, but I never actually call delete on that data. And in fact, it falls out of scope, right? Because each time I enter this loop, I create a new scope. I'm going to create some new space for PTR on the stack. But then I lose that pointer because it gets lost, right? There's no possible way to access that pointer after the loop is finished outside of the loop because the variable is out of scope outside of that curly brace. And if this is confusing to you, please read about scopes in the C++ tour. Okay, so let's fire up the activity monitor. I'm running this use all my memory function now, and what we should see is we should see that process start using more and more memory. So it's running forever right here. I'm going to go up and actually should be using some amount of memory now. Let's go find it. Let's go a.out. Okay, it's currently got 64.9 megabytes of memory. Now 75.5. So it turns out it's actually pretty slow, and that's because calling new is actually not a very fast operation. The computer has to do some work to figure out how to allocate memory to you. All right, so it's not very efficient at like sort of killing our computer. So let's see how we can use our memory even faster. All right, so what I'm going to do now is I'm going to create a struct called foo, and inside of that struct, I'm actually going to put an array of, let's say, 1 kilobyte. This is actually, this is 4 kilobytes, because each integer is 4 bytes of memory, and then I'm using 1024 of them, so I'm using 4 kilobytes of memory. Now, instead of calling new int, I'm going to call new foo. And then I'm going to drop that reference again. I have to change it to foo pointer. All right, do that again. And this is not going to work, I realized, after filming the screen capture because I had forgotten to update the call to use all my memory faster. So we can see it's still going at the same rate it was before. Not really using that much more. It's actually interesting. You can see it's jumping from like 12 to 24 to 50. It's using that exponential kind of growth strategy. The memory allocator on Mac OS X tries to be fairly smart about this. All right, so let's use more memory. This is 16 kilobytes of memory. All right. 16 kilobytes of memory, 4096. Same error, I have it running again, and of course the reason it's not using that much memory is because I haven't actually called it. So let's go over to the other screen, make ourselves actually work with it. We can see again that exponential jump here. All right. And this was when I was scratching my head and thinking, well, why wasn't it going faster? I thought I had allocated a bunch of memory. All right, and then of course I figured out that I actually had to call the right function, use all my memory faster. All right, let's do it. All right, now, 1.66 gigabytes. That was fast. Still going. 6.31 gigabytes. Okay, we're going to kill this before my Mac totally dies. All right. But the key is to make sure we always use delete. All right, and that saves the day. And it turns out that this delete operator will free that memory we initially allocated with new. If you don't free memory after newing it up, there's this term called a memory leak. That's what's going to happen, right? Your program is going to leak memory. All right, so here let's look at a few questions. So let's say you have a variable a, and it's of type int star star star. So a pointer to a pointer to a pointer to an int. Let's see, pointer to a pointer to a pointer to an int. Yep, that's right. Then what is the type of star star a? What is the type of at star, at, star, and I'll start parenthesizing these so it's a little bit more clear. At star, star A. All right, so Okay, just that one for now. But you can try it with mixing in some more stars if you want to get an idea. And then what is the type of star 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 A? All right, and then what is the type of, let's say, star at star star A? All right, so if you can think of what those four things are, then I think you'll be in a good position and you'll have a decent understanding of how pointers work. All right, and then I also want you to think about how you would allocate, or how you would write a function that would allocate an array of some type. So let's say int or something like that. And how would you do that? By allocating an array on a heap and then returning to that pointer. And then what would you do to get rid of it? All right, thanks.